Hello, and welcome to my presentation. My name is Daria Gangart. I'm a PhD student at the University of Birmingham, and today I'll be talking to you about evaluating a phenomenological approach to spin precession in current gravitational wave events. So to start with, how do we describe the spins of two black holes? When we think of two black holes going around each other and orbiting one another, we expect them to emit gravitational waves. The general relativistic effects of this motion means that if the two black holes have individual spins, then those spins will interact with one another, and most importantly, with the orbital angular momentum. This is a very complicated problem with 9 dimensions, including the directions of the spins with regard to one another and also their magnitude. And typically, we like to package all of these spin effects into two characteristic spins, chi effective and chi p. Now, this procedure is great when you're trying to quantify the amount of spin precession in a system. However, it can miss out on all of the interesting spin dynamics that one can get. So instead, in a taxonomy of black hole binary spin precession and nutation, we propose 5 phenomenological parameters that instead describe spin as the motion of L around the total angular momentum J. Indeed, we look at the system where instead of considering the 2 individual spins, we instead consider the motion of L around J. If we split this motion into a polar motion, which we call nutation, and an azimuthal motion, which we call precession. As L goes around J, if there is no nutation, i.e. no polar motion, then it will do so with a constant opening angle theta L. The precession average of this, i.e. the average of theta L over the time it takes for L to complete a motion around J, is what we call the precessional amplitude bracket theta L. As L moves around J, it does so with an azimuthal frequency of omega L, whose precession average value we call the precession frequency bracket omega L. If there is polar motion, then L will move between a minimum and maximum theta L value, and the difference of this is what we call the nutational amplitude, delta theta L. It will do so with a nutation frequency little omega, and when we have polar motion, this will also change the azimuthal frequency. So to complete the picture, we also considered the precession frequency variation, delta omega L. In our analysis, we also considered 3 different populations of isotropically misaligned binary black holes, where we varied the spins of the individual black holes. In green, we have the maximally spinning population, and in orange, the lowly spinning population. As you can see, when we look at the amplitudes of both motions, both the nutational amplitude delta theta L and the precessional amplitude bracket theta L, when we have maximum spins, we get the maximum amplitudes. However, their dependency on Q is very different. When Q is moderate, we expect to have maximal nutations. However, we only have maximum precessional amplitudes when Q is low. This means that if we could possibly differentiate between the 2 different precessional this means that there are 2 different regimes in which we have high nutations and a high precession. One of the things that we wanted to then do as a natural follow-up is to then look for these 5 precessional parameters in the gravitational wave catalog. To say exactly what we want to do is that we want to compare posteriors of our 5 parameters to their priors, just as is done here in this figure from the LIGO-Virgo-Kagro collaboration, where they compared the posterior on the effective precession spin chi p, it's shown in the colored distributions, to the priors, which are shown in the white distributions. So while a posterior that is different from a prior would imply a measurement, we also wanted to expand on this analysis by also considering priors that aren't just uniform in certain parameters, but also contain some of the information that we have on some of the other parameters that our 5 phenomenological parameters depend on, i.e. we wanted to include the fact that we measure chi effective and the masses. The way that we do that is by creating priors that are conditioned on the masses, and then priors that are conditioned on the masses and on chi effective. When conditioning on the masses, this is a very simple process where all we have to do is take prior information on any of the spin parameters and combining them with the posterior information we have on the masses. By doing so, we create our priors that are conditioned on the masses. Then we wanted to expand our analysis to also include the fact that we can measure chi effective really well. Now, chi effective is a combination of spin and mass parameters, which means that we can't do the simple combination as we did for the priors condition on the masses. Instead, we have to consider it sample by sample, where we take a sample from the mass posterior, combine it with samples from the spin priors. Then we calculate the chi effective of this sample and compare it with the chi effective of its posterior. And if the difference between them is smaller than 10 to the minus 3, a chosen threshold, we keep the sample, and if not, we reject it. We repeat this process until we have a prior that covers all of the posterior samples, and then we have a prior that's conditioned on chi effective and on the masses. We then do this analysis, so we formulate these priors for all of the events in the gravitational wave catalog. One of the events that is particularly interesting to look at is GW190412. GW190412 is an event with an extreme mass ratio and a non-zero chi effective posterior. This means that its priors will look very different compared to the uniform priors that are typically used. This event also has a high network SNR, i.e. we can measure quite a lot of its properties, meaning that we can expect its posteriors to be more constrained than for an event with a low network SNR. Across all of our gravitational events, we found that the precessional amplitude is much better constrained than the nutational amplitude. And you can see this here in GW190412, where if you look at the column containing bracket theta L, you find that the posterior is very different from its priors. While for the nutational amplitude, delta theta L, you see that the posterior matches the priors exactly. One thing that is interesting for this event is that due to its extreme mass ratio and non-zero chi effective, we find that each time that we constrain, we condition our priors on the masses and then on chi effective, that this moves our prior distributions around, and yet still because of the we suspect because of the high network SNR of this event, the posterior does not match these prior conditions. And so we think we measure additional information in the event that is not contained in the information of the masses or chi effective. As aforementioned, we repeat this process for all of the events in the catalog, and then we use the Hellinger distance described here below to evaluate to quantify how similar posteriors are to each type of prior, where a Hellinger distance of 1 means that they are very different from one another, and a Hellinger distance of 0 means that they are the same distribution. So here we have the Hellinger distance for bracket theta L, the precessional amplitude, and delta theta L, the nutational amplitude. You can see that across the catalog, the Hellinger distance of the events never goes beyond 0.2, except for the event GW190814 for the nutational amplitude. However, we are able to achieve much more constrained posteriors in bracket theta L, where we see much larger Hellinger distances. Here, I've pointed out some of the most interesting events. GW190412 makes an appearance with a high Hellinger distance in its precessional parameter, as does GW190521 and GW190814. Unfortunately, as I before mentioned, the Hanger distance is not very well constrained across all of the events, which means that we really can't measure nutations at all. However, one area for hope is what we then did is that we did an injection of a maximally nutating event, which had a moderate mass ratio and high spins. And then we put it through the LIGO sensitivity curve for 4. And we found that in this case, if we have a maximally nutating event, we are able to constrain its posterior well away from its priors, regardless of how stringently conditioned those priors are, which gives us hope that in the future, if we have a maximum nutating event, we should be able to detect it. That is all from me. Thank you very much, and I look forward to your comments and questions.